There's a special kind of z-test for when you want to compare two different proportions, and now I'm going to show you how to do that. So here's my example. Researchers want to test the effectiveness of a new anti-anxiety medication. In clinical testing, 64 out of 200 people taking the medication reported symptoms of anxiety. Of the people who were receiving just a placebo, 92 out of 200 reported symptoms of anxiety. Is the medication working any differently than the placebo? Test this claim using alpha of 0.05. Now notice that these are proportions. We have 64 out of 200 and 92 out of 200. We're going to compare these two proportions using a z-test. And the z-test is going to have 6 steps. First, we're going to state the hypotheses. We're going to state alpha, state the decision rule. Then we're actually going to calculate the z, state our results, and then state our conclusion. So first, our hypotheses. Now H0, our null hypothesis, is that the two proportions are equal. And H1, our alternative hypothesis, so what we're testing, is to see if the two proportions are not equal. And the alpha level. I just said use an alpha level of 0.05. Usually it's going to be whatever you set it at, 0.01, 0.03. In this case, we're using 0.05. Next, the decision rule. If we're using an alpha of 0.05, that means that 5% is split up into two different tails, which are 2.5% and 2.5%. That's important because when I look up at the z-table to find my critical value, if there is 2.5% in one of the tails, that means there's 97.5% in one of the bodies because I have to add up to 100%. So using my table, it's important to realize that when the area in the body is 97.5%, the z-score is 1.96, and that's where I get my z. I might have gone kind of fast with that because I've already done it many times. So you can go back to previous lectures on z-scores if you're a little bit confused about how I got to that 1.96. But that 1.96 is what we're going to use as our critical value. We would expect whatever we calculate, the z we calculate, to be between negative 1.96 and positive 1.96. If it's outside of that, we can conclude that it's a rare event and we can reject the null hypothesis. So that's what our decision rule is. If z is less than negative 1.96 or greater than positive 1.96, we are going to reject the null hypothesis. Now actually calculating the test statistic. This is the equation for calculating a z when testing for two proportions. Now, we already know a lot of this stuff. We know that the sample size of both N1 and N2 is 200, and we know the two proportions we're dealing with. We're dealing with 64 out of 200 and 92 out of 200. So we have most of the stuff that goes into that equation already. We just need to find out the pooled proportion. Basically, we're going to average those two proportions using this equation. And when we do that, we find out that p hat is 0.39. So I'm going to put that up here. And now we have the 5 different pieces that go into the equation to calculating z. So I'm just going to go ahead and put those things in there. And when we calculate z, we get a z of 2.869. So when it comes to stating the results, remember that we were going to reject the null hypothesis if z is less than negative 1.96 or greater than positive 1.96. And we had a z of 2.869. That's definitely greater than 1.96, so what we're going to do is reject the null hypothesis and say that the two proportions are different. And that's what our conclusion would be. We're going to conclude that there was a significant difference in effectiveness between the medication group and the placebo group. And then that's how you would actually write it. You'd say z equals negative 2.869, p less than 0.05. That's the official way of writing your result. But your conclusion is just that the two groups were different. And that is a z-test for proportions when dealing with two sample proportions.